On July 12, 2022, humanity opened its eyes wider than ever before. The James Webb Space Telescope transmitted its first deep-field image back to Earth. Scientists expected wonder. They expected beauty. They expected to see the universe as it had never been seen before. What they didn't expect was terror. Buried in that image, and in dozens of subsequent observations, JWST revealed something that shouldn't exist. Something that, according to our best understanding of physics, cosmology, and the very nature of reality itself, is impossible. Galaxies. Fully formed, massive, mature, complex, existing just 300 million years after the Big Bang. To understand why this discovery has sent shockwaves through the astronomical community, why some scientists have called it a crisis in cosmology, why others have begun questioning the very foundations of modern physics, you need to understand what we thought we knew about the universe, and why everything we believed might be wrong. Because what JWST saw in the deepest, darkest corners of space and time isn't just surprising. It isn't just unexpected, it's cosmologically impossible. These galaxies contain hundreds of billions of stars. They show signs of chemical enrichment, stellar evolution, and structural complexity that should have taken billions of years to develop. They're not the cosmic infants we anticipated seeing in the universe's nursery. They're teenagers. Some are practically adults, and they existed when the universe itself was supposedly still a newborn. Imagine this. You're an archaeologist excavating what you believe to be one of humanity's earliest settlements, expecting stone tools and primitive shelters. Instead, you find smartphones, skyscrapers, and nuclear reactors. That's the level of impossibility we're confronting here. The distance between what our cosmological models predicted and what JWST actually observed isn't a minor discrepancy. It's not a rounding error. It's not something we can explain away with a few tweaks to our equations. It's a chasm. And standing at the edge of that chasm, staring into the implications of these observations, astronomers around the world are experiencing something they rarely feel: genuine fear. Not the fear of the unknown, but something more unsettling. The fear that we might have been fundamentally wrong about everything. The fear that the story we've been telling ourselves about the origin and evolution of the universe, the story we've spent a century refining and confirming through countless observations and experiments, might be fiction. Some have called these observations the most significant challenge to the Big Bang Theory since it was first proposed. Others have suggested we're witnessing evidence of physics we don't yet understand, forces and mechanisms operating in the early universe that our current theories cannot account for. A few have even whispered about more radical possibilities, ideas that sound like science fiction but are now being discussed in serious academic capers. But before we dive into the terrifying implications of what JWST discovered, before we explore the theories being proposed to explain the inexplicable, we need to understand the journey that brought us to this moment. We need to understand the telescope itself, the questions it was built to answer, and the universe it was designed to observe. Because only then will you truly appreciate why what it found has shaken astronomy to its core.
The James Webb Space Telescope didn't just happen. It was born from decades of dreaming, planning, engineering, and determination. It represents humanity's most ambitious attempt to pierce the cosmic veil, to see back to the very dawn of time itself. The story begins, as so many great scientific stories do, with limitations, with frustration, with the recognition that our tools, however impressive, simply weren't enough. In 1990, NASA launched the Hubble Space Telescope, and it revolutionized our understanding of the cosmos. Hubble showed us galaxies colliding billions of light years away. It captured the births and deaths of stars. It provided the evidence that confirmed the universe's expansion was accelerating, leading to the discovery of dark energy. Hubble gave us the deepest views of space ever achieved, peering back billions of years into cosmic history. But Hubble had limits, fundamental limits. imposed by the laws of physics themselves. You see, Hubble primarily observes visible light and ultraviolet radiation, the same types of electromagnetic radiation our eyes can see. This works beautifully for nearby objects, for galaxies in our cosmic neighborhood. But when you're trying to observe the most distant objects in the universe, objects so far away that their light has been traveling toward us for over 13 billion years, you encounter a problem. The universe is expanding, and as it expands, it stretches the light traveling through it. Light that was emitted as visible or ultraviolet radiation from distant galaxies gets stretched into longer wavelengths as space itself expands. By the time this ancient light reaches us, it's been shifted far into the infrared spectrum, beyond what Hubble can effectively detect. This is the famous cosmological redshift, and it means that the most distant, most ancient objects in the universe are essentially invisible to Hubble. We can see hints of them, fuzzy suggestions at the very edge of Hubble's capability, but we can't study them in detail. We can't see their structure, their composition, their true nature. It's like trying to hear a whisper from across a crowded stadium. You know something's there, but you can't make out the words. This limitation frustrated astronomers for years. They knew that out there, in the deepest darkness of space, were the answers to some of humanity's most profound questions. What did the first galaxies look like? How did they form? When did the first stars ignite? How did the simple, uniform universe of the cosmic microwave background evolve into the rich tapestry of galaxies, clusters, and cosmic structures we see today? The answers were out there, written in infrared light, waiting to be read. We just needed the right telescope. Planning for what would become JWST began in 1996, just 6 years after Hubble launched. The ambitious goal: build a telescope optimized for infrared observations, large enough and sensitive enough to detect the faintest whispers of light from the universe's first galaxies. Place it not in orbit around Earth like Hubble, but at a special point in space called Lagrange Point 2, nearly 1 million miles away, where it could operate at the incredibly cold temperatures necessary for infrared astronomy. What followed was 25 years of development, innovation, problem-solving, and occasionally crisis. The telescope grew in ambition and complexity. Its mirror, originally planned at 6.5 meters across, dwarfed Hubble's 2.4-meter mirror, providing over 6 times the light collecting area. But a mirror that large couldn't be launched in one piece. Instead, engineers designed an intricate origami-like folding system using 18 hexagonal segments that would unfold in space.
Each segment is coated with a microscopically thin layer of gold, precisely 100 nanometers thick, chosen because gold is excellent at reflecting infrared light. The entire mirror surface had to be engineered to nanometer precision. To put that in perspective, if the JWST mirror were scaled up to the size of the United States, the largest imperfection would be just a few inches tall. But the mirror was just one challenge among hundreds. The telescope needed a tennis court-sized sun shield made of 5 layers of material thinner than a human hair, each layer precisely positioned to create temperature differentials. The sun-facing side reaches temperatures of 185 degrees Fahrenheit, while the telescope side operates at -388 degrees Fahrenheit. This temperature control is crucial because infrared telescopes essentially detect heat, and if the telescope itself is warm, it would be like trying to observe faint stars while shining a spotlight in your own eyes. The budget ballooned from an initial estimate of $500 million to over $10 billion. Launch dates were postponed repeatedly. Critics called it a boondoggle, a waste of money, a project too ambitious to succeed. Some suggested canceling it entirely, but the scientists and engineers persisted, driven by a vision of what this telescope could reveal. Every technical challenge was eventually overcome. Every impossible engineering problem was eventually solved. And on Christmas Day, 2021, JWST finally launched from French Guiana aboard an Ariane 5 rocket. What followed was the most nerve-wracking month in the history of space astronomy. Over the course of 30 days, JWST executed a sequence of 344 single-point failures. Any one of these mechanisms failing would doom the entire mission. The sun shield had to unfold perfectly. The mirror segments had to deploy precisely. Systems that had been carefully folded for launch had to spring into their operational configurations across the cold vacuum of space, nearly 1 million miles from Earth, far beyond any possibility of a repair mission. Engineers watched, helpless, as each mechanism triggered. Each successful deployment was cause for celebration and relief, but there were hundreds more to go. And just one failure would turn a decades-long dream into expensive space debris. Against all odds, every single mechanism worked. Every deployment succeeded. JWST reached its destination, unfurled its giant golden mirror to face the cosmos, and began the months-long process of calibrating its instruments. By summer 2022, JWST was ready. President Biden unveiled the first deep-field image on July 11th, giving humanity a preview. The full suite of initial images was released the following day. The world gasped at the beauty and clarity of those images. The Carina Nebula showed stellar nurseries in unprecedented detail, cosmic cliffs where stars were being born. The Southern Ring Nebula revealed the dying breath of a star, its expelled layers of gas creating an ethereal bubble in space. The Stephens Quintet showed 5 galaxies locked in an intricate gravitational dance, their details sharper than ever observed. But it was the deep field image, officially called JWST's first deep field, that captured the most attention. This single image, focused on a tiny patch of sky, no larger than a grain of sand held at arm's length, revealed thousands of galaxies spanning cosmic time. Some were nearby, relatively speaking. Others were impossibly distant. The image was stunning. It was historic. It was everything scientists had hoped for and more. And buried within it were galaxies that would change everything. Because as astronomers began analyzing the data, measuring the distances to these galaxies, calculating their ages and properties, they realized something was deeply, fundamentally wrong. The universe, it seemed, had not read the script we'd written for it.
The first hints came within weeks of the initial image release. Astronomers working with the deep field data were measuring redshifts, the stretching of light that tells us how far away and how far back in time we're observing. It's a well-established technique, refined over decades. Light from distant galaxies gets stretched as the universe expands, shifting toward longer, redder wavelengths. The more stretched the light, the more distant and ancient the galaxy. Scientists expected to find galaxies with high redshifts in the JWST images. That was the whole point. They expected to see primitive galaxies, small and irregular, showing the early stages of cosmic structure formation. What they found instead defied expectations so completely that many initially assumed the data had to be wrong. In July and August of 2022, preprint papers began appearing on the Astronomy Archive with titles that ranged from cautious to alarming. A population of red candidate massive galaxies at redshift greater than 5. 2 remarkably luminous galaxy candidates at redshift 10-12. And, most dramatically, a candidate massive galaxy at redshift 16. Redshift 16. Let that sink in for a moment. A redshift of 16 corresponds to a galaxy existing just 250 million years after the Big Bang. The universe at that time was 2% of its current age. In human terms, this would be like finding a sophisticated adult in a maternity ward. But the redshifts alone, while surprising, weren't the truly terrifying part. After all, finding galaxies earlier than expected could simply mean that galaxy formation began sooner than our model suggested. We'd need to adjust our theories, certainly, but that's how science works. Observations guide theory. No, the truly disturbing revelation came when astronomers analyzed not just when these galaxies existed, but what they were like. These weren't small, primitive structures. They were massive, incredibly massive. Some of these early galaxies appeared to contain stellar masses equivalent to tens of billions of suns. Their light outputs suggested they were hosting massive populations of mature stars. Spectroscopic analysis indicated they contained heavy elements, metals forged in the cores of previous generations of stars. And they were structured. They showed disk formations, signs of rotation, evidence of organized galactic dynamics. Some even appeared to have prominent bulges, dense stellar populations at their centers that typically take billions of years to form through galaxy mergers and gravitational processes. Let me put this in perspective. According to our standard cosmological model,
called lambda CDM. The early universe should have been relatively smooth and uniform. In the beginning, matter was distributed almost evenly throughout space, with only tiny variations in density. Over time, gravity amplified these tiny variations. Regions that were slightly denser pulled in more matter, becoming denser still. Eventually, these growing clumps of matter formed the first stars, then small galaxies, then larger galaxies through mergers. This is a slow process. It takes time, lots of time. The first stars, called population 3 stars, were expected to form perhaps 100 to 200 million years after the Big Bang. These would be massive, short-lived stars composed purely of hydrogen and helium. They would live, die, and explode as supernovae, seeding space with the first heavy elements. Only then could subsequent generations of stars form to create the chemical diversity necessary for complex galaxies. Small galaxies would form first, then gradually merge and grow into larger structures over hundreds of millions to billions of years. This hierarchical model of galaxy formation has been our standard understanding for decades, supported by numerous observations and simulations.
According to this model, at 300 million years after the Big Bang, we should see small proto-galaxies, irregular blobs of stars, perhaps containing a few million to a few hundred million stars, primitive structures, just beginning their long evolutionary journey. Instead, JWST saw galaxies that looked like they'd already completed that journey. Galaxies that, according to our understanding, shouldn't have had time to form. By September 2022, more papers were flooding the archives. One study identified 6 massive galaxy candidates at redshifts between 7.4 and 9.1, corresponding to when the universe was just 650 to 550 million years old. These galaxies appeared to have stellar masses between 10 and 100 billion solar masses. To understand how problematic this is, consider the rate at which galaxies can grow. Stars form from gas clouds. The rate of star formation is limited by various physical processes: how fast gas can cool and collapse, how efficiently it can be converted into stars, how much gas is blown away by stellar winds and supernovae. These limits are well understood, grounded in solid physics. When you run the numbers, when you calculate the absolute maximum rate at which a galaxy could possibly form stars under ideal conditions, you get a limit. And these observed galaxies appeared to exceed that limit, not by a little, by factors of 10 or more in some cases. It's like finding an oak tree in a forest and measuring its trunk to find it would take 500 years to grow that large, but then carbon dating the wood and discovering the tree is only 50 years old. The math doesn't work. Something is fundamentally inconsistent. One particularly troubling example came in November 2022 when researchers announced the discovery of what they called CEERS 93316, a galaxy candidate with a photometric redshift, a redshift estimated from the colors of light, of approximately 16.4. If confirmed, this galaxy would have existed just 235 million years after the Big Bang. The galaxy appeared bright, suggesting a large population of stars. Initial estimates suggested it might contain 1 billion solar masses of stars. To form that many stars in just 235 million years, you'd need an average star formation rate of about 5 solar masses per year every year since the Big Bang. That might not sound like much, but consider, our Milky Way galaxy, with its hundreds of billions of stars, forms new stars at a rate of about 1 to 3 solar masses per year currently. And the Milky Way has had over 13 billion years to build up its current population. For this early galaxy to have achieved such mass so quickly, it would have had to maintain an incredibly high star formation rate from nearly the moment the first stars could physically form. But it gets worse. Star formation isn't 100% efficient. Much of the gas in a galaxy doesn't become stars. It's heated by radiation, blown away by stellar winds, consumed by black holes. When you account for these inefficiencies, the amount of gas this early galaxy would have needed to start with becomes enormous.
In many cases, these galaxies would have needed more gas than should have been available in their region of space. The cosmology community was buzzing with excitement and concern. At conferences and in online forums, astronomers debated the implications. Were these measurements correct? Could there be errors in the distance estimates? Were we perhaps misinterpreting what we were seeing? Some suggested that the photometric redshifts, which estimate distance based on the colors of light without detailed spectroscopy, might be unreliable. Perhaps these galaxies weren't as distant as they appeared. Perhaps some were just dusty nearby galaxies, whose light had been reddened in ways that mimicked the signature of extreme distance.
Follow-up observations provided both relief and renewed concern. Some of the most extreme candidates, like Sears 93116, with its claimed redshift of 16.4, were indeed found to be less distant than initially estimated when observed with spectroscopy. The spectroscopic redshift came in at about 4.9, placing it much later in cosmic history, a case of cosmic mistaken identity. But many others were confirmed. Throughout late 2022 and into 2023, spectroscopic observations verified that numerous massive mature galaxies did indeed exist in the universe's first billion years. The problem didn't go away with better data. If anything, it intensified. In February 2023, a landmark paper was published analyzing 6 massive galaxies observed by JWST at redshifts between 7.4 and 9.1, corresponding to 650 to 550 million years after the Big Bang. The paper's conclusion was stark. These galaxies were so massive, containing so many stars, that they were challenging the standard cosmological model. The authors calculated that these galaxies, collectively, represented an unreasonably large fraction of all the matter that should have been available in the early universe. In the standard model, most matter is dark matter, the mysterious substance that doesn't interact with light. Only about 16% of the total matter is ordinary, baryonic matter that can form stars and galaxies. But to produce these observed galaxies with their measured stellar masses, you would need to convert essentially all the available baryonic matter in their regions of space into stars with near-perfect efficiency. Not 50% efficiency, not 70%, more like 100%, or more in some cases. It's impossible. It violates basic physics. Gas can't convert to stars with 100% efficiency. There are fundamental limits imposed by thermodynamics, by the pressure support of gas, by the energy input from the stars themselves that blows gas away. And yet, there the galaxies were, staring back at us from the abyss of deep time. By mid-2023, the observations kept coming. JWST discovered a galaxy designated JADES-GS-Z13-0 with a spectroscopically confirmed redshift of 13.2, placing it 330 million years after the Big Bang. This galaxy appeared to be forming stars at a robust rate and already showed signs of chemical enrichment with elements heavier than hydrogen and helium. Another galaxy, JADES-GS-Z11-0, was confirmed at redshift 11, about 430 million years after the Big Bang. This one appeared particularly unusual. It wasn't just forming stars, it showed evidence of a supermassive black hole at its center, actively feeding on surrounding matter and shining brightly as a quasar. Supermassive black holes are typically thought to grow over billions of years, either through the mergers of smaller black holes or through the steady accretion of matter. Finding one so early, already weighing millions of solar masses, presented yet another timing problem. How could such a massive black hole have formed so quickly?
The discoveries continued throughout 2023 and into 2024. Each new observation added to the picture of an early universe that was far more active, far more mature, far more complex than we had anticipated. Galaxies at redshift 10, 12, even 14 were being discovered and studied. Many showed disk structures, organized rotation, chemical enrichment, and stellar populations that simply shouldn't have had time to develop. One particularly striking finding came from studying the light from these early galaxies in detail. When you break down the light from a galaxy into its component wavelengths, you can identify the spectral signatures of different elements. Hydrogen has its characteristic pattern, so do helium, carbon, oxygen, nitrogen, and the rest of the periodic table. In the earliest galaxies, you'd expect to see mostly hydrogen and helium, the primordial elements created in the Big Bang itself. Heavier elements only form inside stars through nuclear fusion, and when those stars die and explode as supernovae, these elements are scattered into space to be incorporated into the next generation of stars. This process takes time. Multiple generations of stars need to live and die to build up significant quantities of heavy elements. In astronomy, we call all elements heavier than helium metals, and the abundance of these metals in a galaxy tells us about its stellar history. Early galaxies should be metal-poor, containing only trace amounts of these heavier elements. Later galaxies, like our Milky Way, are metal-rich, enriched by billions of years of stellar evolution. But JWST found metals in these early galaxies, significant amounts: oxygen, carbon, nitrogen, even heavier elements. The chemical signatures suggested these galaxies had already experienced multiple generations of star formation, multiple cycles of stellar birth and death. They'd had time to enrich themselves chemically. Except they hadn't had time. Not according to our models, not according to our understanding of how quickly these processes can occur. By early 2024, papers were being published with titles that reflected the growing unease in the community. The impossibly early galaxy problem, trouble at the earliest times, a crisis in cosmology. One researcher put it bluntly in a press interview. If these observations are correct, if these galaxies are really what they appear to be, then something is very wrong with our understanding of the universe. Either our cosmological model is incomplete, or we're missing some major piece of physics, or we need to seriously reconsider what we think we know about the early universe. The terror wasn't coming from the discovery of something unknown. Astronomers love discovering the unknown. That's the whole point of science. The terror was coming from the discovery that what we thought we knew, what we thought we understood, might be fundamentally incorrect. It's the difference between exploring a dark cave and discovering a new species of bat versus walking into your own home and discovering that the laws of physics work differently in your living room. One is exciting. The other is existentially disturbing. And the observations kept coming. More massive galaxies, earlier epochs, more contradictions. Each new JWST deep field image revealed more problems, more anomalies, more reasons to question. The universe's first billion years, which we thought would be a time of slow, gradual assembly, looked instead like a period of frantic, impossibly rapid evolution. It was as if someone had pressed fast forward on cosmic history, compressing billions of years of evolution into a few 100 million years. Some galaxies showed morphologies, structures that looked remarkably similar to galaxies in the present-day universe. Elegant spiral arms, distinct disks, prominent bulges. Finding these features so early was like finding a fully formed butterfly emerging from a cocoon that had only been spun an hour earlier. The data also revealed another mystery. Many of these early galaxies appeared exceptionally bright, far brighter than expected. When you observe a distant galaxy, its light has been traveling toward you for billions of years. During that time, the light gets spread out over an increasingly large area, making the galaxy appear dimmer. This is one reason why distant galaxies are hard to observe.
But some of these JWST galaxies, despite being incredibly distant, were bright, unexpectedly bright. This suggested they were producing enormous amounts of light, either through incredibly high rates of star formation or through some other process we didn't fully understand. One possibility that gained traction was that these early galaxies might be hosting a population of extremely massive stars, far more massive than any stars we see forming in the present-day universe. These hypothetical supermassive stars, perhaps weighing hundreds of solar masses each, would burn incredibly hot and bright, producing enormous amounts of ultraviolet light. They would also have short lifetimes, perhaps just 1,000,000 years, but during that time, they would make their host galaxies shine brilliantly. The problem is, we don't have definitive evidence that such supermassive stars can form. Current stellar formation theories suggest there are upper limits to stellar mass, around 150 to 300 solar masses, imposed by the radiation pressure from the star itself. Stars more massive than this limit would theoretically blow themselves apart before they could finish forming. But maybe conditions in the early universe were different. Maybe the lack of heavy elements, which act as coolants, in gas clouds allowed larger clouds to collapse into more massive stars. Maybe we need to revise our understanding of stellar physics for the extreme conditions of the early cosmos. Or maybe something else entirely is going on. By 2024, nearly 2 years after JWST's initial observations, the astronomical community had accumulated enough data to be certain. This wasn't a fluke. This wasn't a measurement error. This wasn't a case of a few unusual outliers. The early universe was consistently, repeatedly showing us galaxies that were too massive, too mature, too structured, too enriched, and too abundant. Thousands of astronomer hours had been spent checking and rechecking the data. Multiple independent teams had analyzed the observations. Different methods had been used to estimate distances and masses. The results were robust. We were seeing something real, something that didn't fit our models, something that demanded explanation. And the explanations being proposed ranged from subtle adjustments to our cosmology to radical reimaginings of fundamental physics. Some were scientifically conservative, requiring only modest changes to existing theories. Others were revolutionary, calling for complete overhauls of how we understand the universe. But before we explore those theories, we need to understand why these observations are so terrifying. We need to understand exactly what's at stake, what parts of modern cosmology are being challenged, and why astronomers are using words like crisis and impossible to describe what JWST has shown us. Because the implications go far beyond just needing to update a few parameters in our models. What JWST has discovered strikes at the very heart of modern cosmology. It challenges the story we've been telling about the universe's origin and evolution. It questions whether we truly understand the fundamental forces and processes that shaped the cosmos. It makes us wonder, if we were this wrong about the early universe, what else might we have gotten wrong?
To understand why JWST's discoveries are so deeply unsettling to astronomers, you need to understand just how solid, how well established, how thoroughly tested our standard cosmological model has been. This isn't some speculative theory based on a handful of observations. It's a framework that's been refined over a century, tested against countless observations, and consistently confirmed by independent lines of evidence. The standard model, called lambda CDM, stands for lambda cold dark matter. Lambda represents dark energy, the mysterious force causing the universe's expansion to accelerate. CDM represents cold dark matter, the invisible matter that provides the gravitational scaffolding for galaxy formation. Together with ordinary matter, radiation, and the initial conditions from the Big Bang, this model describes how the universe evolved from a hot, dense, uniform state 13.8 billion years ago to the rich cosmic landscape we see today. Lambda CDM isn't just one person's idea. It's the culmination of observations from multiple telescopes, satellites, and experiments. It's been tested against the cosmic microwave background, the afterglow of the Big Bang itself, measured with exquisite precision by satellites like COBE, WMAP, and Planck. It's been tested against the large-scale distribution of galaxies across billions of light years. It's been tested against the abundances of light elements forged in the first minutes after the Big Bang. It's been tested against supernova observations that revealed the accelerating expansion of the universe. Every test for decades has confirmed the model's predictions. Not perfectly, but well enough that any discrepancies could be attributed to measurement uncertainties or minor modeling details. Lambda CDM became the standard model not because astronomers were wedded to it ideologically, but because it worked. It made predictions that were borne out by observations. Until now. What JWST has shown us isn't a minor discrepancy. It's not the kind of small tension that can be resolved with better measurements or slight adjustments to parameters. The galaxies JWST observes in the early universe are so numerous, so massive, and so mature that they fundamentally conflict with what Lambda CDM predicts should be possible. Let's break down exactly where the conflicts arise. First, there's the timing problem. In Lambda CDM, structure formation is a bottom-up process. Small structures form first, then merge to create larger structures over time. The first stars ignite around 100 to 200 million years after the Big Bang. These gather into small proto-galaxies over the next few hundred million years. These proto-galaxies then merge repeatedly over billions of years, gradually building up the large galaxies we see today. This hierarchical assembly is driven by dark matter. Dark matter, which makes up about 85% of all matter, doesn't interact with light, but does interact gravitationally. In the early universe, dark matter began clumping together under its own gravity, creating invisible halos, concentrations of mass that acted as gravitational wells. Ordinary matter fell into these dark matter halos where it could cool, collapse, and eventually form stars. But this process takes time. Dark matter halos need time to grow. Gas needs time to fall into them, cool down, and reach densities high enough for star formation. Stars need time to form, live out their lives, and die. Subsequent generations of stars need time to form from the enriched material. Galaxies need time to merge and grow. The JWST observations show this process happening far too fast. Galaxies with stellar masses of tens of billions of suns are appearing just 500 or 600 million years after the Big Bang. That's like planting a seed and expecting a full-grown tree by next week. When you run the simulations, when you model galaxy formation under Lambda CDM using our best understanding of physics, you simply don't get these massive galaxies forming this early. The simulations can produce small galaxies at these epochs, certainly. They can produce proto-galaxies, structures in the process of assembly, but not the mature, massive systems JWST is observing.
Second, there's the abundance problem. It's not just that we're seeing a few unexpectedly large galaxies. We're seeing many of them. JWST's deep field images reveal that massive galaxies in the early universe appear to be more common than our models predict. In Lambda CDM, the probability of finding a very massive galaxy at very early times drops off steeply. Massive structures are rare early on because they require the merger of many smaller structures, and mergers take time. The further back in time you look, the fewer massive galaxies you should see. But JWST is finding them in numbers that seem inconsistent with these predictions. Some estimates suggest that there are 10 times more massive galaxies at redshift 9 or 10 than Lambda CDM would predict. Other analyses suggest the discrepancy might be even larger. This abundance problem has a technical name: the stellar mass density problem. When you add up all the stars and all the galaxies JWST observes at these early times, you get a total stellar mass density, a measure of how much matter exists in the form of stars per unit volume of space. And this density appears to be too high compared to what Lambda CDM predicts. Remember, in Lambda CDM, there's only so much ordinary matter available to make stars. Most matter is dark matter, which can't form stars. Of the ordinary matter, only a fraction ends up in galaxies, and only a fraction of that converts into stars. When you work through the numbers, you get firm predictions for how much stellar mass should exist at different epochs. The JWST observations appear to exceed these predictions. It's as if there's more matter available to make stars than there should be, or as if the star formation process was far more efficient than we thought possible.
Third, there's the maturity problem. Even setting aside the issues of timing and abundance, there's the puzzling fact that these early galaxies look too evolved, too structured, too chemically enriched. When you run simulations of early galaxy formation, you get chaotic, irregular systems. Gas clouds collapse, stars form in bursts, supernovae explode and blow gas around. The whole process is messy and turbulent. It takes billions of years for this chaos to settle down, for galaxies to develop smooth disks, for stellar orbits to organize into regular patterns. But JWST is seeing organized structures, disk galaxies with rotation, systems that appear to have already undergone significant evolution. It's seeing chemical enrichment that requires multiple generations of stars. It's seeing evidence of supermassive black holes that should take hundreds of millions to billions of years to grow. The universe at these early times should be a cosmic construction site, all scaffolding and incomplete structures. Instead, it looks more like a finished neighborhood. Fourth, there's the brightness problem. Many of these early galaxies are luminous, shining brightly despite their distance. This brightness requires enormous rates of star formation or the presence of other energetic processes like actively feeding black holes. High star formation rates require large quantities of cold gas, but in the early universe, gas is typically hot, heated by shocks as it falls into dark matter halos and by radiation from the first generations of stars. Hot gas resists collapse. It needs time to cool down before it can form stars. There are astrophysical processes that can enhance cooling and allow gas to collapse faster, but they have limits. The JWST observations seem to push against these limits, suggesting star formation rates that approach or exceed what should be physically possible given the conditions in the early universe. Now, each of these problems individually might be explainable. Maybe we've underestimated how quickly dark matter halos can grow. Maybe star formation was more efficient than we thought possible. Maybe there are feedback processes we haven't properly accounted for that accelerate galaxy assembly. But the problems aren't individual. They're all happening together. The same observations showing us galaxies that are too massive also show them existing too early, appearing too often, looking too mature, and shining too brightly. It's the combination, the systematic nature of the discrepancies that's truly concerning. It suggests we're not just missing one piece of the puzzle. It suggests the puzzle itself might be the wrong shape. Let me give you an analogy. Imagine you're a detective investigating a crime, and you have a solid theory about what happened. Your theory is supported by fingerprints, DNA evidence, security footage, and witness statements. Everything fits together nicely.